In this introductory video, we will have the overview of the contents of the course. So, we will be teaching differential equations. We will be learning, you will be learning differential equations basically both the ordinary differential equations and partial differential equations. Okay. So, this is the syllabus. So, basically what we consider is the syllabus is divided into a few sections, few modules. So, if you look at in the first module, we can have first order ordinary differential equations. We will study these first order ordinary differential equations and its methods, both linear and nonlinear. Most of the nonlinear equations cannot be solved analytically. So, those are the equations for which you can solve completely. We will have those solutions, or we will look at most of the equations that can be solved in a closed form will be dealt in this first order ODE. So, we will see all the methods, what are the available methods that are available for the first order ODE. We will see in the first module. In the second module, then we will move on to second and higher order ordinary differential equations. So, in this mostly initially we will look at some form of nonlinear equations of second order, those you can directly integrate. We will see only one or two methods is possible. Later on we move on to linear second order ordinary differential equations, we look at it, and then we study its properties and then how to find its solutions, both homogeneous and non-homogeneous equations. Okay. This is what we see in the second module. Even for second order and higher order equations, not all equations can be solved. So, in a closed form. So, what we do is when the linear equations with variable coefficients, if the coefficients of the linear second order or higher order equations are functions of x, they are not constants, then you can expect power series solutions. So, we will introduce power series solutions and special equations in physics which you study as a special case of these power series solutions, okay, that we study in the third module, and we develop theory of Sturm-Liouville based on the properties of second order equations, second order linear equations and its solution. That is basically finding eigenvalues and eigen functions corresponding to the differential operator and then its properties. Based on using these properties, we will make use of these properties and we will solve a linear partial differential equations in simpler domains such as rectangular or circular or elliptical domains. Simpler domains, you can solve linear partial differential equation by a simpler technique called separation of variables. We make use of the Sturm-Liouville theory of ODEs for ODEs and use that to solve partial differential equations. That is what you do in the last module. So, this is what briefly what we are going to study or what we are going to learn in this course on differential equations. Okay. So, the textbooks that we follow are basically Kreyszig. I may not follow exactly the contents of Kreyszig, but you may find most of the material in this book. And for reference books, you can look into this Agarwal and Regan, Introduction to ODE, and Piskunov for part of a certain calculus. And also you can look into any partial differential equation, for example, Tang. There is a book called Tang, I did not show here. You can also look at this book. This is also okay. Partial differential equations for scientists and engineers. Dover publication. It's Farlow, S.J. Farlow. You can look into this book. Or there is a book called Tang, Mathematical Methods for Scientists and Engineers by Tang. So, you have 3 volumes. I think third volume you can find partial differential equations. Okay, that I have not shown here. So, you can look at, there are many books you can go through. So, most of the contents will be available in those books. So, in this introductory lecture, we will just introduce what is a differential equation. So, start with the definition and its solutions. What do you mean by solution? What is its general solution? And what are the solutions other than general solution one may find for the ordinary differential equations? Okay, that we see in this video. So, let us start defining what is the differential equation. A differential equation is a relation between a function and its derivatives. Function is depending on the domain. So, function is defined on the domain space, that is a variable x, that is called independent variable. Okay. So, if f is the function defined on the real line, so fx is a function, x is the independent variable, f if you view it as f of x as a variable, f is dependent variable. So, we call y as a dependent variable, x as independent variable. If you have a relation between y and its derivatives, say n derivatives, nth order, then any relation between y dash up to yn derivatives and x, relation between all these variables, is actually called a differential equation. So, formally we write the definition: any relation capital F of this variable, dependent variable y dash up to n derivatives. My notation is like this: y in the superscript, if I put a bracket, that means the derivative, okay. Dash, this is dash. So, this now we have independent variable x. So, if this is equal to 0, any relation, okay, any relation f like this, if you have a relation like this, what exactly this means? That is, f is from, we have 1, 2, 3 up to n. So, r power n plus 1. I have how many variables, how many dependent variables that can take real values, y dash and y n derivatives. So, r n plus 1 in cross x takes also real values. So, you have r to r. Any relation f that is from this domain to this domain satisfying f of this relation f equal to 0 is called a differential equation. It's called an ordinary differential equation. Or ODE. Now onwards we call ODE. Why it is ODE? Because you have one linearly independent, you have one independent variable x. If you have more than one independent variable, let us say if I have a relation like this, if I have a relation, any relation f from r n, so I do not know exactly how many I will have. So, if I take two independent variables, so I have r2. So, two independent variables, instead of x I have x1 and x2, that takes two values here, to finally r, and y is the dependent variable. Dependent variable is always 1, okay, because it is a scalar differential equation. So, you have y and its n partial derivatives with respect to x, with respect to x1 and with respect to x2. So, you can have for each x1 I have n plus 1. So, you have 2 times. So, any relation like this satisfying f of y, yx, yx1, yx2 and y x1, x2, so like this and so on, all combinations. Similarly, y, so you have only second derivatives, right. So, you have so like that you go up to n derivatives of, depending on the order, okay. So, if you have n derivatives of y means y let us write y x1 power n, y x1 x2 power n, okay. X1, that means y x1 up to n times, like that, all the n derivatives, dou square dou n y divided by dou x1 n times, that is what is this one, okay. So, like this if you have, and x1 x2 are two linearly independent, two independent variables, this relation is called partial differential equation. Partial differential equation. Or PDE, okay. So, what we do is we go only two derivatives. Variables can be two. Okay. So, it is going to be variables independent variables are 2, and if the order I can go to only two derivatives, that is the second order partial differential equation in two variables. Okay. Because you have more than one variable, if you have, then it is more than two independent variable if you have more than one. So, you have two here. So, this is a partial differential equation. So, when do you say a differential equation is linear? A differential equation is linear if I will just give you. So, when you say that f is linear in y, y dash and all nth derivatives. In these variables, if f is linear, something is linear, if it is linear in y means you will see only y variable just as y with some coefficient which is function of x, then it is linear. If it is y square, root y, y power anything, these are all nonlinear. Okay. Once you see that, immediately you can say that it is nonlinear. Okay. So, we can define what is linear and nonlinear. If the function f is linear function in the variables in y, y dash, yn for ODE. Okay. For ODE, we can say this. If this is a linear function in these variables, we say that the ODE is linear. Otherwise nonlinear. Same thing with the PDE. Okay. So, it's all its dependent variables y x1, that means dou y by dou x1, dou y by dou x2, dou square y by dou x1 x2, all these and derivatives, they should stay in the equation as it is, not its squares, not its any powers. Okay. Then it is linear PDE. So, in this course we start with the first order ODEs. First order ODEs, we try to give you a solution methods. How do we solve it? If you have f y dash, so I have a first order, y is the dependent variable, x is the independent variable, which is equal to 0. So, this is the general first order ODE. Okay. When it is given, nothing is given means what is the domain? X belongs to full R, y and y dash belongs to full R. So, x and y in the plane, x takes the full values, y takes the full values. So, solution means any relation for y on x, that is any function, any curve yx that satisfying this relation is called a solution of the differential equation, ordinary or partial, whatever. If you take the partial differential equation, you simply look for y acting on x1 and x2. Okay. In the domain where x1, x2 are the variables, y of x1 and x2 is the solution of the partial differential equation. If it satisfies y and its all derivatives and you substitute into the relation, it has to satisfy. Okay. So, here it's a ODE, so domain is single variable, so it's a curve. If it is in PDE, you will have a two variables, so its solution is defined over a plane. So, that means you can it is like a surface that satisfies the equation. Surface, right? Z equal to f of x1 and x2, some function of x1 and x2. Z is that, x1 and x2 is the plane, third dimension is z. So, z equal to f of x1 and x2 or y of x1 and x2, if that satisfies this relation, that is means that you have a surface that satisfies the partial differential equation, that is called solution. Okay. So, we start with this first order ODE. This is what is. So, how do you, so we do not know the methods if it is in this implicit form. If the equation is in this implicit form, it may be difficult to solve this equation. So, if we can solve for y dash in in an explicit form. So, still so if you have an explicit form like this, where still I replace this f as f is still not known, x I will write independent variable, I am writing first and then dependent variable. So, if you have in this form, okay, this is a implicit form. Implicit form you may not be knowing its solutions, not always, okay. Very few methods, very few are available to solve the implicit equations, okay. Only standard equations you can solve, so just one or two, Clairaut's equation, Lagrange type equations. You can look into the syllabus, you can look into the textbook, you can look into the reference books, you can see implicit equations, certain implicit equations, how they can be solved, okay, if you are interested. Otherwise, if you want solution methods for many equations, you want them in an explicit form like this. Explicit form for y dash equal to f of x y, where f is arbitrary function. So, now we start with the method separation of variables method. First method, separable method, separation of variables. What does it mean? So, if I have f of x y, if I have something like f1x into f2y. So, these variables f x and y are separated. So, I have separate nice form. If you have in this nice form, if f general f, if it is in this nice form, I can easily solve. So, your equation is dy by dx equal to f1x into f2y. So, whenever you see an equation, you have to see a domain. So, this implies a domain is everywhere it is defined. So, when I do not write the domain, whenever you see the equation, it is defined on certain domain. So, domain means a values x takes wherever it is defined, okay. X takes all the values, if nothing is given, x takes all the values, and the depending variable can be, it can be there, it can be any value in the real line. So, mostly independent variable, what the values it takes is the domain, okay. So, nothing is given means x belongs to full R. So, now if I divide this dy by f2y equal to f1x dx, you can see that this immediately when you write like this, f2 of y should not be 0. So, you are in some domain in xy plane where f2y, certain values of x where f2y is 0, you should avoid, that is not in your domain, that is the meaning when you divide it, okay. So, formally we do like this. So, once you do this, now you can integrate this equation. So, you have a dy, so variables are separated, these are functions of y, these are functions of, right side is functions of x. So, you can divide it f2y dy and you integrate. So, integration will give you f1x dx. Once you do the integration, so you will have integration constant c. So, this is actually your general solution. This is the general solution of the equation. So, the general solution, so general solution means, so you have an arbitrary constant, any solution that involves an arbitrary constant. Is called general solution. Okay. So, when you integrate, you have an integrating constant, that is arbitrary constant. So, it is a general solution. So, if it is a nonlinear equation like this in the implicit form f y y dash x equal to 0, if it is in this form, you may have, you may not have, you may get the general solution as a certain form that involves an arbitrary constant. It does not mean that these are the all solutions. You may have some other solutions, they are called singular solutions. Singular solutions. So, what are the singular solutions? I will just explain. So, what you have is, if you have a general solution that involves an arbitrary constant, what are these for first order ODE? These are solution curves with the parameter c, that arbitrary constant. So, you have a parameter family of solution curves. If the envelope of these curves, if you can find, if it exists, it is a solution. It is a solution of the differential equation that cannot be gotten by this general solution. Okay. So, such solutions are called singular solutions. We do not deal with this course, we only want what we mean by solution is a general solution, finding the general solution. When I say solve the differential equation, I only want you to find the general solution of the differential equation, okay, not the singular solutions, but I think you should know how to find the singular solutions. Okay. So, I will give you examples how do we solve this one. So, whenever you have this solution, there are many ways to there are ways to get these singular solutions. The idea is you got rid of this y dash by just simply calculating dou f by dou y dash equal to 0. So, this is one equation, given equation, and this is another equation. These two equations, if you from this, if you remove your y dash, what you get is the solution in terms of x y. That is a curve. That curve is called singular solution. Okay, that is one way. But if the envelope exists, that is the solution. So, then the envelope exists, then if you solve these two equations, then you can expect to get your envelope, that is a solution, singular solution. But the best way is you solve the first one and you have a general solution, let us say phi of x y some constant c equal to 0. So, suppose this is the general solution of the given equation. So, we do not do this, let us say, okay. So, we do not do this. So, instead you have a general solution and then you try to differentiate this dou phi by dou c equal to 0. So, look at these two equations, eliminate c will give you the singular solution. Okay. So, if the envelope exists, okay, envelope of phi of x y c equal to 0, c is arbitrary. Okay. If envelope exists, if this envelope exists, then you solve this to get the singular solution. Okay. Then this is satisfied. Okay. So, this will give you singular, these together if you eliminate c, that will give you singular solution. So, we have just defined what is a differential equation and what is the meaning of general solution. So, we have seen that general solution is if it is a first order equation, if you have a solution that contains an arbitrary constant, that is called a general solution. Okay. And these are not the only solutions. If it is a nonlinear equation, it can have some other solutions, that is called singular solution, that is also what we defined. So, we will demonstrate with an example in the next video what you mean for singular solutions. Okay. So, once you have a family of solutions, general solution, that may generate an envelope. Okay. If you view geometrically, the general solution is a family of curves that may generate a new envelope. So, that can be a solution of the equation. So, that is what we will see. When the envelope exists, that can be a solution, that is called singular solution. We will demonstrate with an example in the next video. Thank you.